Alright, 1.3 exponential functions. Let me write the definition. Alright, let a be a positive real number other than 1. The function f of x equals a to the x power is the exponential function with base a. Alright, let's do an example. Graph the function y equals 2 times 3 to the x power minus 4. State its domain and range. Alright, before we do anything, let's pull out the calculator. Let's take a look at what 3 to the x power looks like. Alright, looks something like that. Now, when you subtract 4, you know it's going to go down 4. And when you multiply by 2, you know it's going to stretch. Okay? Yeah. There you go. Okay? Let's go ahead and graph that. And goes down 4. So there's an asymptote at -4. Normally it's 0, but it moved down 4. Imagine it's supposed to hit there. And the graph looks something like that. There we go. Okay, so the domain is the x values, and this actually continues this way all the way for infinity. So the domain is from negative infinity to infinity. The range, it starts at -4 and then goes all the way up to infinity, but it does not include -4. There we go. Alright, you guys go ahead and try this one. Alright, this is the answer you guys should have gotten. You go ahead, feel free to pause if you need to take a look a little longer. Okay, example 2. Find the zeros of this graphically. Alright. Let's pull out the calculator again. Y equals 5 minus 2.5 to the x power. Alright, so it looks like that. Alright, now, the way you find zeros on a calculator, you're going to go to calculate, which is the yellow word right over trace, so hit second, calculate. 0 is number 2. Left bound. Alright, so this is what you want to do. You want to get somewhere close to the 0, because you know the 0 is right here. So somewhere close to the 0, so there or there would be fine probably, for the left bound, and then somewhere on the other side of the 0. Make sure you don't accidentally end up right on the line. Okay? Then when it says guess, hit enter, and it will give you the 0. So in this case, 1.76-ish. Alright, so let me graph this first. So it looks something like this. Yeah, good enough. Okay, and the 0, I don't remember what it said. 1.76, approximately. Okay. Alright, you guys go ahead and try this one. Alright, this is the answer you guys should have gotten. Once again, left you guys a lot more space than you needed. Rules for exponents. You guys know most of these. I'm just going to write them down. If a is greater than 0 and b is greater than 0, the following hold for all real numbers x and y. If you multiply exponents with the same base, you add the powers. If you divide exponents with the same base, you subtract the powers. If you multiply an exponent by an exponent outside parentheses, like as shown here, you multiply the powers. If you multiply, whoops, I made a mistake here. Hold on. There we go. If you multiply two exponent with the same power, you can pull out that power like this. Likewise, if something is to a certain power, you can distribute that power to all terms inside the parentheses. Alright, example 3. Use the data in the table and an exponential model to predict the population of the United States in the year 2012. Okay. If you notice, the ratio between any year and the previous year is approximately 1.01, roughly, each year. Okay? So if we were to assume that this trend were to continue, this is what we do. This is the number we're looking for. We're looking for the next year. All of these are about 1.01. So we have an equation. X over 301.6, we'll say equal to 1.01. If I multiply both sides, $304.6 million. Now, we could do this over and over again. This would be for 2008. We could do the same process over and over again until we get 2012. It would be easier, however, if we were to create an equation. 2012 comes 10 years after 2002. And in 2002, we had 287.9 million people. Okay? We're multiplying by 0.01 or 1.01 just like we did over here. But because it's 10 years later, we're going to multiply it by 1.01 10 times. Alright. I'm going to use the other calculator for this one. Alright, 1.01 to the 10th power gives us that, times 287.9. 318.02 million. And this is for 2012. Alright, you guys go ahead and try this one. Alright, these are the answers you should have gotten. If you calculated the ratios with these numbers exactly the way they did it over here, you should have gotten these decimals. I used 1.034 since that repeated itself and some of the numbers were above that, a couple of the numbers were below that. Seemed like a good number. If you use like 1.035 or if you found the average or did something else, that's fine. So this is one possibility of a model. The initial value times this number, the ratio, to some power. Okay, in 2015, if you plug that in, you should get 3,348,000 or 3,348,000. Alright, example 4. Suppose the half-life of a certain radioactive substance is 20 days and that there are 5 grams present initially. When will there be only 1 gram of the substance remaining? Alright, so if we look at this, after 20 days, this is going to be cut in half. After 40 days, it's going to be cut in half again. So after 20 days, it's going to be cut in half once. After 40 days, it's going to be cut in half twice. After 60 days, 3 times, etc. So the model I'm going to be using is this right here. 5 times 1/2. T is the number of days divided by 20. So after 20 days, 20 divided by 20 is 1. So it's being cut in half once. After 80 days, 80 divided by 20 is 4. So it's being cut in half 4 times. That's why I'm dividing by 20 here. Okay? Alright, now we could solve this algebraically. We'd have to use some logs for that. Or we could solve this graphically. Okay, here we go. So I'm going to plug this in. I've got 5 times 1/2 to the x over 20 power. Let me zoom out a little bit. Actually, zoom out even more. There we go. Something kind of like that. Maybe 100 would have been fine. Gosh. There we go. There we go. That's much better. Okay. So what I need to do here is I need to figure out where y equals 1. So let's just add another line here. I'm going to zoom in. There we go. I want to know this intersection point here. So what I'm going to do here is, let's see. I'm going to go to calculate. I'm going to find intersect. First curve. Second curve. Guess. Right there, when y equals 1, this is what x equals. So 46.44, approximately. Okay. Alright, you guys go ahead and try this one, and when you think you have the answer, hit play. Alright, this is the answer that you guys should have gotten. Feel free to pause here and look it over if you need a little more time. Alright, example 5. Use the population table below to estimate the population for the year 2000. Compare the result with the actual 2000 population of approximately 281.4 million. Okay. Alright, first thing you're going to do is you need to enter this data into your calculator. The way you create a table is like this. You're going to go to Stat. You're going to go to Edit. This is going to be your X values. This is going to be your Y values. Now, rather than putting in the years, I'm just going to enter in numbers 1 through 12. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10,